In this situation, we have a student who's doing an experiment with this paper toy that you can cut out and fold up. And they pick it up and they hold it in a particular spot, and he drops it. It gives it enough time to get to terminal velocity, and then measures the terminal velocity over this distance right here, which we are told is 0.75 plus or minus 0.01 meters. And what the student does is makes heavier and heavier toys by adding additional sheets of paper when he makes it. So the graph we have down below, we should oizerga it. Origin 0, 0. Y-axis is meters per second. Velocity in meters per second. And we see it goes by 0.01s. The x-axis is n, and it has no units, and it goes by ones. The intercepts, if we were to draw a best fit line through these points, we might have an intercept here, a y-intercept of about 0.13 meters per second. And that is when n is 0. That means no paper will have a terminal velocity of 0.13 meters per second, which makes no sense at all. So in this region right here, something happens, because what we know is you can't have less than one sheet of paper. It's either 1 or 0. And so that's the phenomenon of having an integer, a discrete set of numbers in that case. So that's our intercept. We can read, of course, velocity in n. The gradient is delta v per n. So that means with every increase of one sheet of paper, it is the change in v per one sheet of paper, which we can see is fairly constant, at least up until 5 sheets of paper. And the area then is meters per second times n, which has no units. So it still has the units of meters per second, but we can see if we were, as we increase n, the area increases. What exactly that is, I don't know. But at least that's what it's telling us. We've taken a look at it. We've considered it. Okay, so that's just the information we have with our oizerga. Fixed distance 7.5, and we know that the delta t is 5%. Is the 5% uncertainty. And so that's just making sense of what's going on. So what we see is as we increase the weight, the terminal velocity increases, and then it kind of seems to steady out. It looks like it's going to steady out by once we get past 5 sheets of paper. So we wanted to calculate the absolute uncertainty and the terminal speed of the paper for n equals 6. So we go back to the graph, and n equals 6. So we've got a terminal velocity of 0.40 for n equals 6. And we want to know the absolute uncertainty in that velocity. Well, what we can see in the beginning is we're given an uncertainty, an error bar, for n equals 1. And that uncertainty is plus or minus 0.01 meters per second. And somehow we need to get it at the end. Now, we can see that there's a fixed uncertainty with the time. There's a fixed uncertainty with the distance, with the distance, the vertical distance, but it's a percentage on the time. And if the velocity is the distance, delta z over delta t, and this is fixed, at plus or minus 0.1, and this is a percent, well, that means that the uncertainty in the velocity is also going to change. So to keep track of all of this, there's a number of quantities. It's easy to get lost in them, and a number of different kinds of uncertainty. So what we have for our quantities is we have delta Z, we have delta T, and we have V. And we have two different types of uncertainty for each of those. We have the absolute uncertainty, and we have the percent uncertainty. Now in Z, we know it's plus or minus 0.01, the absolute. And delta T, we know it's 5%. And V, we know neither, but we're being asked to find the absolute uncertainty in the velocity. Well, what we know is there's a propagation going on here. We have the average velocity is delta Z over delta T. And so whenever we have a propagation going on, the best thing for us to do is to have this percent uncertainty and this percent uncertainty and add them, and that will become the uncertainty in the velocity. So the U percent V is going to be the U percent delta Z plus the U percent delta T. So we know this one is 5%. We just need to find the percent uncertainty in delta Z. Well, the percent uncertainty in delta Z is the absolute uncertainty divided by the value of Z times 100. Well, we know the absolute uncertainty is 0.01. The value of Z is 0.75. And that gives us a percent uncertainty of 1.3 repeating percent. So that means to get the percent uncertainty in V, we have a percent uncertainty of 6.3%. But that doesn't give us the absolute uncertainty. We need the absolute uncertainty. Well, the absolute uncertainty is related to the percent uncertainty over the value of velocity times 100. What we're looking for is the U absolute. So the U absolute of the velocity is the value of the velocity times the percent uncertainty in the velocity divided by 100. So that average velocity that we found on the previous was 0.40. That's the actual value at 6.40. So 0.40 times 6.33 divided by 100. And that works out to be 0.025 meters per second. And if you remember, we can only report one significant digit, so that means we're looking at 0.03 meters per second. So what we need to do is take these pieces and put them in to combine for our answer, but this is basically the entirety of our work there for part I. And now we're asked to draw that error bar for n equals 6. So it's plus or minus 0.03. And we can see it goes that way and that way. And so as you've seen in the many graphs you've created in class, when you use a percent, the error bars get larger as x increases. And so that's what we'd expect to see here as well. And it's actually pretty large, that uncertainty that we get. And now we're asked to draw the best fit line, which we have already done. Now, the thing to keep in mind about a best fit line, a line of best fit, it could be straight, it could be curved. It doesn't say draw a straight line that best fits the data. It says draw a line. And so that's parts A and B. We'll continue on in the next segment